So to begin the demo, we want to see that it, like essentially with the ease of use as well, we don't want them to have to like do anything to utilize it. It's just sort of a plug and go sort of thing. Obviously there was things we need to change because of the laptop, but to make sure that it still functions as a lamp, we wanted to not fall over. Like obviously if you have a lamp that's a long arm, if you put too much weight on the arm, the lamp falls over, the light can't handle, or the arm can't handle it. So
the way you want to do this demo is that we don't know. Susan and I are customers. We don't know what the background is. Okay. So what you're doing is you're pitching the product to the customers. So go with the assumption that everything works, and then this is what the customers wanted. These were your specs, and this is what we are showing.
Okay. So we're showing that it functions as a lamp in the sense of it doesn't fall over, so it can just function like that. So obviously it can hold itself up, which is good in the sense that it would be useless without it.
The base is rather heavy and compared to the shade, so it has a very low center of gravity, so it was not easy to tip over.
The second demo function is that this, because it's a lamp and it's going to be placed in dorm rooms and used by people, it has to be safe, meaning that because there is heat surrounding it, that the lampshade itself has to be safe and it won't catch on fire or anything. So to do that, if you were to look inside, you would see that the inside is covered in mylar, which is a flame retardant material. It's like shiny and cool and stuff. So that is to protect the fabric so that the fabric doesn't catch on fire from the heat of the light inside of it. So it creates for a durable and safe lampshade.
Okay.
We also have a motor system on the bottom of the shade. It has 3 motors attached to 3 mirrors, and the rest of the mirrors are fixed to the bottom of the shade. We wanted customers to have the option of the light going all the way to the bottom or to the top. So we have an electrical circuit that attaches to the motors.
So where are the mirrors?
They're in the up position right now.
They fold down. So
this is the desk lamp mode.
When you turn it on, the motors rotate down, so the light reflects off the mirrors, and the top flips up, so the light goes up.
And there's a lens at the top, where it will disperse the light out from the source. So like the light goes to the bottom mirrors, and then it goes back up into the lens, back out.
Yeah. So.
Can probably demonstrate. Yeah.
So it's just a flippable switch, which changes from the 2 modes. This is desk lamp mode, which has the mirror pointing downward, so it reflects all the light back into the desk, and it has the mirrors on the bottom moved upward, so it lets the light through. And then for the other mode, it closes the mirrors on the bottom, which reflects the light up, and it reflects around inside due to the mylar, and it directs all the light through a lens, which refracts light. And it flips the top mirror upward to allow the light through.
Okay.
So.
And right now it's not as impressive, the light distribution. That's mostly due to the light that we had to change inside of it. But we can measure now using the lux meter the lux produced by this in a dark room, and also the addition of it with the standard room lighting to see if it's improved off the baseline values that we've collected.
Okay. Yeah, measure.
Okay.
Where's the lux meter?
So we can measure first the light at the desk surface for like if it's going to be functional.
How much is it now?
No.
With the mirrors at the bottom.
With the mirrors at the bottom, it is reading 87.6
What?
lux.
Lux. Okay. Now, and how much is it reading on the top?
Directly over it.
Yep.
It is reading. Oh, gotta change the value. Roughly 7. Now it's at 842. 842 lux.
And the previous one was how much?
Previous
82.
So,
Okay. Now
underneath.
change the flap.
I think it tripped. Yeah, that's one of the issues with the power supply from the laptop. But
Okay.
Now at the base it reads roughly 820 lux, 820, and the top reads 0.
Okay. Okay. And what was the reason that with the mirrors on the bottom, it was giving some value and not completely shutting it off?
yeah, so it's not a perfect seal. If you were to look at it when it's closed, it has gaps in it, and also on the sides, the mylar doesn't completely cover the side, so some of the light leaks out. And it bleeds through the fabric a little bit. So there's still some light going downward into the desk.
And why is it going? Is it workmanship or is it by design or?
It's a little bit of both. One is because of the mirror arrangement and having to get them so precise, each one being slightly different with the way we manufactured it, we couldn't get it as exact as needed to be. So there's some error there, but also a little bit of light is good to come out the bottom so that the user can still see the switch easily and be able to use it.
Yeah.
So is that part of the customer requirements that when the flaps are at the bottom, there's still some light so that you can see the switch?
We wanted it to be easy to use for the customer. So though the initial condition of having the entire bottom completely sealed up was the idea, that wasn't very feasible. So we kind of tied it in to fit with other customer requirements and needs
But
to make it a
yes,
better product.
one requirement was ease of use, and this
Right.
is how we then.
It was more of an intuitive decision.
Okay.
Also, the original plan before it was to use a normal universal lamp socket, so you would be able to use bulbs.
Mhm.
And if you were to look now at the type of light that we have to use, it's just a flat LED that points completely downward instead of a bulb which emits light in all directions. So that's
yeah.
one of the things we have to change due to the RPI rule of not using above 24 volts. So.
Okay. And is the switch, is it like a 1-0 kind of a thing, either completely shut? Can you make it partially
It's
closed?
It's basically completely shut or completely closed.
And what's the reason for that?
Because, the voltages I have to use for this are lower than like with the other circuit, and so the motors actually move quicker. But if in the other system, the idea was to have a slider control the position of the motors, and have a button be pressed when you want to use the slider or not. So it would allow you to, according to the position of the slider, have the motors be completely up or completely down, or in the middle, according to where you move the slider.
So the slider would have adjusted the position of the mirrors.
Yeah,
Yes.
that was the idea.
Okay. And because you cannot,
It moves too quickly for that to be possible.
I got it.
Yeah.
Because you
Also-
need the full power of the motor to
Yeah.
really move
Well,
it.
also the motors move in 18-degree steps, so you can't have completely accurate movement. It's either 18 or nothing. And with I'm not sure exactly how
Do
much
you have
they move.
where's the slider?
I don't. It's in my backpack actually, but it's
Okay.
not in the system. Yeah.
Sure. So in the initial system, where would the slider be placed?
In place of the switch, because
It replaces
the
back.
switch would actually be replaced with circuitry. So
So
there's
it'll go
no.
like this.
You do not have to do this. You just press a button,
Oh, I see.
and it basically switches on within the circuit.
So what the switch does is it takes the motor from zero, so
Essentially, yes. If you're-
0 to 1, but the slider actually
would have
controlled the movement of the two.
Yes.
Okay.
If you can move them partially now, if you're quick enough, but they just move too quickly to be for that to be possible. Essentially, it's not a precise movement. So actually, I don't know if I have it in this bag. Might be in my room.
Okay. Can you bring it tomorrow to the
Yeah.
class?
Right here.
Perfect. Anything else you want to demo over here?
If you like a closer look at the motor movements, we can turn off that light, turn on the room lighting, so you can get a better look at that.
On the
you,
inside.
can we do that?
Yes,
what?
of course.
Can you show that?
turn on room lighting, turn off the lamp.
Turn on the
the
lamp,
motors.
turn off the lamp.
Turn it off.
Turn off the
Yeah.
lamp.
Yeah.
So we can actually see the movement.
Zoom in.
Okay. Okay, now keep it like this. And now turn off this lamp and turn this light off.
Turn this on.
You want it facing the desk?
You want
or
this
facing-
lamp?
Want it open?
No.
Just
Turn
off?
this light off. Okay. Now show me like if I want to put the sliders down and just have the top light on. Oh, and what's the reason you're taking the switch back over there?
It actually works. So the way it's set up now is that the motors are stalling. They're still taking current, but if you lift the switch, it fixes that. So that would have been done manually or automatically by the Arduino if we had it's called a relay. So it takes place of that switch, but it can be.
Okay, now put it back again. Alright. Okay. And how many reflectors are there
At the bottom.
at the bottom?
Or
6.
Yeah, there's 3 moving, and on the side, there's these
3
little-
triangular
yeah.
pieces.
And
that
why?
fill in the gaps. So they'll have the U-joint system.
The initial idea was to have a U-joint system to have 6 mirrors turning at the exact same time. However, over time we realized that would be both difficult to accomplish and also unnecessary because
Why?
with how the mirrors are structured right now, to have them all move at the same time, they clash with each other and it would cause a ton of problems. So the U-joint system was scrapped entirely and replaced with a simple 3-motor system. And the 3 parts that do not move, the little triangular mirrors, those are determined to be, they were basically included as fillers of the gap for when the mirrors are down, because it's very insignificant during this shine down, and very significant during that shine up mode.
Oh, these are the flaps, okay. Can you put the flap? Let me do it. Oh, so you have a, okay. That's how you're getting a hexagon, alright. Okay, I got it. And this is all mylar.
On the inside.
On the inside.
What is this?
That is
It's just
fabric.
fabric.
This fabric?
Yeah.
And this is not flammable.
No.
No.
Well, it's in case
Definitely not.
the
this
mylar
type.
prevents it from heating up.
Also, the LED doesn't get hot,
Right. It's
But-
cool lighting.
and incandescent would have.
Yeah. Are we supposed to use only LED or can you use any light?
Well, the
Well,
idea
the
was
original,
to have a bulb socket that would work with any
light
uh,
bulb.
any universal bulb, but we had to replace it with this.
An accent light, because that's the only thing that would have a plug that we could disconnect from the light to allow it to thread up the arm without having to solder,
Right.
Which we
Or
can't
deal
do.
with the voltage
Yeah.
that we're not allowed to
which we're not
work
allowed
with.
to do.
Can you turn the lights on, please? The room lights. Alright, so all the circuitry is inside the box.
Yeah.
In the base.
Yeah, we got
Yes.
rid of-
And
Would
this
you
is-
like to?
Yeah, could you please
Okay.
turn it off and
Turn
show
off
me?
all-
So you can see we got rid of the microcontroller
Okay.
because we couldn't power that as well as the motors with the laptop, and there's no use to use it without the slider anymore. So we decided to plug. We could control everything directly with the breadboard connected, so it connects the motors to the switch, which is why it continuously draws power if you have the switch set down, which is why I've been lifting it up. But with the Arduino, it would cut the power because it would operate the switch automatically. So
And in the original system, that Arduino would have been inside the box.
yeah, controlling the button as well as the slider. So
And,
and the digital switch, which would control the motors.
which would have been over here instead of this.
Well, this, I mean, the switch would not be. It's called a relay, and it would not be visible to the user. It's just a
Sure.
component. So
But this switch on
Yes,
top.
it would be right here. You see this one right here? That's where it
I
would
see.
be. Yeah.
But right now this is not working.
It's
Yeah.
not functional because
Okay,
of
got
what
it.
We had
happened.
already
Yeah, we
cut
already
it
had
at
it
that point.
cut, so
So essentially, this thing wouldn't be there at
no,
all.
it
Just
wouldn't. Yeah.
Right.
it'd
Just
just
the
be
switch.
that,
It'd
a
be a
button and a
switch.
well,
slider.
but then how do you control the
Well, no, the-
relay for adjusting the position?
So that was part of the slider system.
And where would
Uh,
the slider be?
It would be. It was originally intended to be in the center.
Okay. And how?
and a
What would
button
be the
which-
design like? Would it be
So yeah, it goes. You press
like
a
just
button.
like a slider kind of a thing?
Yeah, it's like a normal slider. You just press a
Oh,
button,
I see.
and it tells it to control the motors.
Okay.
And the position of the slider would dictate where the angle of the motors relative to the horizontal. So having the slider all the way in one direction would have the motors be up, and the other would have it be down.
And it was a push slider, not like a turn.
It was like a slide, like I don't know.
Yeah.
I don't know what you mean by
It's a
push
push
slider.
slider.
Like a
Yeah.
yeah,
I'd
like
want
a
to
dimmer
try
switch. You push it up and up. Okay.
We're bringing it down tomorrow.
So it will be just like in rooms where you have like a slider where you
Yeah,
can
like-
adjust the.
Yeah,
Right.
except
The
not,
switches with
Uh,
sliders on them.
not
So
for
that-
brightness, but for the mirror system. Like it doesn't directly.
Mm-hmm.
It's
So
for direction
so
of
that
light.
so instead of
Direction of
instead
light,
of the
yeah.
brightness of the lamp, what you're doing out here is you're using that same slider system.
Yeah,
For
to
the
control
mirrors.
the mirrors.
Right.
Yeah.
Essentially,
It
that's
Which
what
directly
in turn
changes the
affects
brightness.
the light.
So the power consumption in this particular system is still high because you're running the bulb at constantly at the highest.
Yeah, but it is a. I don't know. Chris bought the.
Yeah.
LED.
Well, let me rephrase the question.
Okay.
When you measured the
The lux.
when you measured the lux, the top one was a different value, at the bottom was a different value.
Right.
So conceptually, to control the amount of power that's being consumed, okay, with the slider, you're putting the reflectors at the bottom, and could you also have control the power to the lamp so that
So that was actually the very original, like the first idea of the slider to directly control the
Just
brightness
the-
of the lamp. That was
Okay.
definitely too complicated.
why was it too
The
complicated?
circuitry involved in that was actually got started with it, but I couldn't finish. But yeah,
Okay,
it was.
but
very-
that was the original.
that was the original idea.
And when you say circuitry was complicated, why was it complicated?
because you can't normally when you have a dimmer. If you have a dimmer in a low voltage, like a slider in a low voltage scenario with an LED, it just increases the resistance. It decreases the current, and you dim the LED like that. But with with AC power, 120 volts, you can't do that with a slider. There's too much power, so you basically have to build a circuit that detects when the AC voltage crosses 0 and connect that to the Arduino, which tells that circuit to cut the power to the lamp for like a few nanoseconds. So basically that's how you dim a normal AC incandescent or any type of bulb that powers.
So you
to the
dim it.
wall.
You dim it essentially. The AC power, the voltage remains the same, but
Everything, like instead of having a normal sine wave basically for voltage, it's like you in the middle of the wave you have to build a circuit that cuts that power.
and that's what the
starts it
dimmer
again during the
does.
wave. That was what the circuit was. That was the original intention of the circuit,
Sure, but what? How does the dimmer work?
like that.
Like that.
There's
So
there's
it
different
doesn't
methods.
go to peak voltage. It
It-
just cuts it off.
It cuts it before, and that's
Okay.
how the slider controls where in that wave power gets cut.
Where
So-
along the x-axis the power gets cut.
Yeah. So, that was definitely very hard to do, as well as not being allowed by RPI. So
Sure, but conceptually it could have been done, and you could have used.
conceptually, yes.
Could you have used two sliders, one for dimmer and the other for? Would that have made
Yeah,
it easier?
Well, it's still not allowed by RPI, but it would.
No, but-
yeah,
But the
It would have
from a
been
circuitry
possible.
part of it.
yeah, it definitely would have been possible. Yeah.
So because then it gives you more degrees of freedom
Yeah, you
in
can-
terms of.
Yep.
And the circuitry would have been easier.
It still would have been very difficult, but it.
Difficult from RPI, but
Yeah.
in terms of the circuitry to control, because now you have more control. Because I could now, like in one scenario, I could have the entire thing up,
Mhm.
and I have the maximum amount of light because I want the reflected light to be pretty bright. In another scenario, I could have dimmed the light also, so the reflected light on top could be.
Yeah.
Yeah. So we're having two different switches.
Yeah. That would have been possible, definitely.
Would have been possible. Okay. All right. And with the two different switches, could it have been done at RPI?
Mm.
No.
You can't build a dimmer system without messing with 120 volts, unless you get a off the shelf dimmer, which I looked into. They're about $40, $20 to $40. They're about this big, and like this, and you still have to solder the connections directly to something that plugs into the wall. So even then, it wouldn't have
And
been
then
allowed.
so it's the regulation at RPI which doesn't allow you to mess around with
Essentially, yeah.
with the wall, which prevented you from doing it. Okay. So in your report and presentation, do mention that your original intention was that,
Mhm.
where you could have more control, and you could not do it, and how would the circuit would have looked if you were able to do that.
Yep.
Okay, so mention that, and you already have a circuit in mind how it would have looked, right?
Yep. It's,
Would it be easy to draw that circuit?
it's already in my computer.
It's all, so make sure it's in the report.
Yep.
You said this was the ideal system, we should have given us more freedom, we tried this, and we were told not to do it, and this is the system that we came up with. Okay, so that way we know that from a engineering design standpoint, you met all the customer requirements to begin with in your original design. Then your plan B design also you met it, but you had to put other controlling through the computer. Now, in your original system, computer doesn't have any play in it, right?
No, you don't even plug it
Because
in.
your
Yeah,
the software is the Arduino.
It's all controlled by the Arduino.
Arduino. So that's where the whatever coding and everything
Yep.
is over there. Okay, got it. Okay, mention this in the report. Okay. And by the way, great job that you were able to do this. Surely. Okay, that's fantastic. I knew you guys could do it. So this is fantastic. I love it. Okay, can you bring this to the class tomorrow,
Yeah,
please?
of course.
And bring this also to the class.
For the drawing or
No,
Oh,
to
the
show
to
that
show
you
it
guys-
off.
Oh, right, yeah.
to show that it works.
Okay.
Okay, because this is, yeah, you can bring the lux meter also and measure it over here and measure it over there, right? Because that will go much better than showing a video.
Mhm.
Okay, you have the video as a plan B, but demo the whole thing tomorrow.
Okay.
Okay?
Mhm.
Um,